there'll be just, I guess I have a couple announcements. So I'm handing out right now the penultimate problem set. There'll be one more problem set handed out next week. It'll be due during exam period, and that's fair because it's sort of in lieu of an exam. Two other announcements. So I will be out of town next Thursday, which is ostensibly the last class of the semester. I've arranged a secret special surprise guest lecturer for you as usual. So that'll be exciting. So class is normal next Thursday, but the topic will be something exciting. And one other announcement is that I did miss one lecture early on in the semester. And so I was going to schedule a makeup lecture. And so it's just going to be next Tuesday, or the following Tuesday at the usual time and place. Okay. So even though ostensibly classes end next Thursday, there will be one more lecture, which is the following Tuesday. I think it's December 7th. Is that the right date? December 7th? December 8th, yeah. Good. And that's just replacing one lecture that I missed early on in the semester. Okay, so let's go ahead and get started. So far what we've really been building up to in this class is a discussion of the quantum theory of electrodynamics. And we're really now in a position to write down the Feynman rules and start doing calculations for the quantum theory of electrodynamics. So I'll just remind you, so we worked out the Lagrangian of electrodynamics. It's a theory of a photon, whose kinetic term is just the usual Maxwell term, coupled to a four-component spinor psi. And the coupling between these two fields is completely determined by the gauge principle. And it involves this object called a covariant derivative, which is defined to be the normal partial derivative plus a coupling term that leads to an interaction, which we can just read it off. So it's proportional to the electric charge. And it couples one photon to two spinors. And it couples them specifically through this gamma mu term. So this is much like the coupling between the gauge field and the electron field in scalar quantum electrodynamics. The only difference is that because we now have this gamma matrix here, when we write down the Feynman rules, there are going to be a few more indices to keep track of. So today, what I want to do is I want to write out the Feynman rules in their full glory, in all detail for quantum electrodynamics. And then the next three lectures, the rest of this class, are going to be devoted to doing some explicit computations. So we'll do, for example, electron-electron scattering, electron-positron annihilation into muons or electrons, which is the case that you'll do on the problem set. We'll do Compton scattering. And then we'll end with sort of our first real loop calculation in quantum electrodynamics, where we'll compute the anomalous magnetic moment of the electron, including its first quantum correction using QED. This is probably the most famous, probably the most important computation in quantum field theory. So although it's been a sort of build-up, a long build-up throughout this semester, the next week and a half, 2 weeks are where we really get some payoff. We'll be moving at the rate of approximately 1 to 2 Nobel Prizes per lecture. Okay, so there's a lot of good stuff that we're going to be covering. Okay? So let's just work out the Feynman rules. So a scattering process that we might want to study in quantum electrodynamics would involve, say, some electrons and positrons along with photons, and is computed, as usual, by summing overall Feynman diagrams which are built out of the following ingredients. So first of all, there are some set of external legs associated to the incoming electrons, positrons, and photons and outgoing positrons, photons, and electrons. So for every incoming electron, we draw one incoming spinor line with an arrow to denote the direction that charge is flowing. Here, arrows, as we discussed last time, denote the direction that negative charge is flowing because some silly person decided to give electrons negative charge rather than positive charge. And here, this blob here denotes the rest of the Feynman diagram. Okay, so the incoming particles I'm going to write as coming in from the left. That blob is the rest of the Feynman diagram where that electron is undergoing some interactions. And that electron will have some polarization described by some four-component spinor U. And for every external incoming electron, we need a factor of that polarization of the photon. Okay? And by including that factor, we'll be taking into account the dependence of the scattering process on the polarization of that incoming electron. Correspondingly, the outgoing electrons get factors of U bar. Okay. Incoming positrons get factors of V bar, and outgoing positrons get factors of V. And again here, the charge arrows are arrayed so that they point in the direction that negative charge is moving. Okay. And here, of course, the polarizations U and V for these electrons and positrons are functions of the momentum of these electrons and positrons. And all of the external legs need to be labeled by the momentum of the corresponding particle. Okay. So you send in an electron with a particular momentum and a particular polarization. Similarly, if you have an incoming photon, then you'll send it in with a particular momentum and polarization. Photon lines are denoted by squiggly lines. And for every incoming photon, you get the polarization 4 vector, the factor of the polarization 4 vector. And for every outgoing photon, you get a factor of the complex conjugate of the polarization. And so the idea is that once you specify the incoming and outgoing particles, you have these external legs. And these external legs are connected by propagators, which we have already computed. These are essentially the two-point functions of the fields written in momentum space. So, for example, there is a photon propagator, which is equal to I over p squared times g mu nu. And here there is a mu and a nu index associated with the two ends of this propagator. Remember, a photon has a 4-vector index, and so the two-point function of the photon has two of these indices. So the propagator really should be thought of as an object with two indices. Similarly, the spinor propagator should be thought of as an object with two indices, so a 4x4 matrix that acts on spinor indices. But we don't like to write those indices explicitly when we can help it, so I'll just write it as 1 over p slash plus m. Oops, it's p slash minus m. Sorry, a typo in my notes there. And, of course, just connecting these external lines by propagators is boring. That just gives you the free theory. We also have interactions. And the interaction vertex, well, there's only one interaction in quantum electrodynamics. What does it look like? Well, here it is right here. So it's minus E times A mu psi bar gamma mu psi. So that leads to an interaction where one photon comes in and an electron and a positron come out. And that is given by a factor of minus IE gamma mu. Note that this is really an object with three different kinds of indices. It has a mu index that corresponds to the incoming photon, and it has two spinor indices corresponding to those two external legs. Okay. So it's really, if you think about a set of 16 times 4, so a set of 64 quantities here. So, if we were to write everything out in components, there would really be 64 different types of interactions, right? One for each, 4 different polarizations of the photon, and 4 different polarizations of each of the 2 different external spinors. So it's a good thing that we use these sort of abstract index notations, or else the Feynman rules would be very complicated indeed. So these are the ingredients that enter into our Feynman diagrams. And when we connect them, we need to enforce momentum conservation at the vertex, at each interaction vertex, as well as charge conservation, which just means that we need to align all the arrows so that when you connect propagators and vertices, the arrows line up and point the same direction. So this lets you determine the momentum for each leg. But, of course, there are various different indices that need to be contracted up. And fermion indices are going to be contracted, that is to say multiplied, along the lines of charge flow. So in particular, you start with either a U bar or a V bar, so represented by an incoming positron or an outgoing electron, so that'll either give you a V bar or a U bar respectively, and ending with a U or a V, so that'll be either an incoming electron for a U or an outgoing positron to give you a factor of V. And so the expressions in your Feynman diagram will involve a U bar or a V bar multiplied by a bunch of gamma matrices coming from these interaction vertices, or factors of 1 over P slash minus M coming from the propagator, and ending with a U or a V. Finally, for each loop in the Feynman diagram, we integrate over the undetermined momentum flowing through that loop, and we trace over fermion or gauge theory indices for the particles flowing around the loop. And there's the final subtlety that we also have to include a factor of -1 for each fermion loop. This came from some of the anti-commutation relations that we worked out earlier. So this gives you a final expression for the diagram. And we finally need to remember that because when you have external particles that are fermions, they have odd statistics. So you get a factor of -1, a relative factor of -1, when you compare two different diagrams where you exchange external fermions and this is relative to some sort of ordering of the external fermions, which once you fix it determines all of the relative minus signs. So you just choose some particular ordering of the fermions, and then when you look at other diagrams where the external fermion momenta and polarizations, say, are interchanged, you'll get factors of -1. And we'll see this quite explicitly in a little bit. So these are the Feynman rules for quantum electrodynamics. I've written them down in their full glory. I'm really not going to write them down again. So we've, I think, derived reasonably carefully every different possible ingredient in these Feynman rules. And the next several lectures are going to be devoted to working out some of these the consequences. But maybe before I proceed, I should just pause and see if there are any questions. Speak now or forever hold your peace. Yes.
Okay, in the interaction Lagrangian, we just have the one interaction.
Mm-hmm.
But I guess I'm kind of wondering why the coupling term in the covariant derivative doesn't have anything to do with an interaction.
That interaction is, so the coupling term in the covariant derivative is that interaction term.
Okay.
Right?
Okay.
So if I set E equals to 0, this would just be a free photon and a free electron, and they wouldn't talk to one another. The coupling between the electron and the photon is determined by the gauge principle, which was the principle that I had to replace all of my ordinary derivatives with covariant derivatives. This is the kind of magic of gauge theories in electromagnetism. This is the magic of the way of thinking about electromagnetism from the point of view of gauge symmetry, is that once you impose this gauge principle, it completely determined what interaction you could have between the electron and the photon. And it completely determined this interaction term. So I read off that interaction term by expanding out this term and just sort of rewriting it out.
Yeah, I just missed it. I thought it said Lagrangian free. So
No. That's Lagrangian of QED. Yes. Good. Yes. Question.
In the electron propagator, does it matter to which side the charge flows?
Yes, absolutely. So, for example, if you changed the direction of the charge flow, you would get a minus sign. In particular, I mean, when we work this out explicitly, so actually, we're going to encounter a very similar point in just a minute. Good question. Yeah. That's just to say that a little bit more clearly. Remember, this is, say, the propagator that connects a psi with a psi bar. The one that connects a psi bar with a psi is given by the complex conjugate. Yes. Question.
In your rule
Sure.
10, maybe it's just confusing wording, but it says here that you can track them along the lines of charge flow.
Yes.
So that would be
You
opposite the direction of the arrows on the graph.
Exactly. So we're going to do an explicit example in 1 second of that. Yes. Good. Yes. In particular, you can track them in the direction so that at the end of the day you get a scalar, right? Because the scattering amplitude is supposed to be a number, right? It's supposed to be some complex number u squared to get a probability. So it has to be a number, and so that means you have to get something of the form u bar matrix u if you want to get a number out at the end of the day. So this is really if I wanted to, I could have not said that rule, and then you could have probably figured it out on your own by demanding that you get a scalar. But when we start using these, you'll see exactly how this works. Yes, there was another question. Was that? Yeah.
In the vertex, is it the two scalar arrows an incoming electron and a outgoing positron?
Yes. So this could either be interpreted as an incoming electron and an outgoing positron, or an incoming positron and an outgoing. Oh, I'm sorry. What did I say? Yes, an incoming positron and an outgoing electron. Yeah. Right. I mean, of course, how you orient it, your interpretation of it will depend on how it's oriented. Right. So, for example, for example, sorry, what did I say? I think I said that completely backwards. You can either, sorry, charge is conserved, of course. So this is what happens when you teach. You know, it's very hard to give a class where you lecture for 25 lectures for 80 minutes at a time without saying a few things that are completely idiotic. So I misspoke, actually. You know, it's of course, charge is conserved, of course. So it's either an a photon turning into a positron-electron pair, or a positron-electron pair coming in and creating a photon, or an electron coming in and an electron going out, or a positron coming in and a positron going out. Those are the 4 different stories that you would associate with that picture, all of which conserve charge. Okay. I think I just misspoke when I said it was an electron coming in and a positron coming out. Right? Like you see, like let's put it this way. If I drew this picture for you, sorry. If I drew this picture for you with incoming particles on the right and incoming particles on the left and outgoing on the right, you would say it's a photon creating a positron and an electron. If I drew this picture for you, you would say it's an electron and a positron creating a photon. If I drew, say, this picture for you, you would say that it's an electron emitting a photon. Or if I drew this picture for you, you would say it's a positron emitting a photon. Or rather, a photon and a positron coming in together to form a positron. So, right. Here, let's write it. So, you know, you might have 4 diagrams that look like this. Right. And the bottom 2 would describe the emission of a photon by an electron and a positron, respectively. Yeah. Good. Any other questions? Okay. So one comment that I'll make right away is that in nature there are actually many different kinds of charged particles. Electrons, protons, fermions, and so forth. So really, we could have several different species in our theory of Dirac spinor field So, for example, if you wanted to describe a theory that of electrons and muons interacting with photons, then in addition to, so you would now have two different kinds of spinor field that we could call psi e and psi mu. So this would be a theory of electrons interacting with muons. Muons are particles that are identical to electrons in every respect, except they're heavier. So they have a mass mu, which is large compared to the electron mass. But they have the same charge. And so the theory that I'm writing down here is the theory that would describe the interactions of electrons and muons via the exchange of a photon. And so you could use this, for example, and this is an example that I'll work out in some detail, to study the scattering of an electron from a muon. So what would the amplitude for this process be? Well, let's say that we have an electron with momentum P, with an initial momentum P1 and a final momentum P1 prime that interacts with a muon, which has an initial momentum P2 and a final momentum P2 prime. Then, so what is that scattering amplitude? Well, this is very similar to the process we studied last class in Yukawa theory, where we had two charged particles interacting via the exchange of a scalar particle, the pion instead of via the exchange of a photon. So what is the interaction? Well, you get two factors of IE coming from the interaction vertex. So you'll get a minus E squared. Then you'll get a factor of I. Sorry. So coming from the photon propagator, so you get a factor of minus I coming from the photon propagator here. That minus sign will kill the minus sign that you get from the IE gamma mu squared. And you get, so this process will depend, so let's say that the incoming particles have polarizations U1 and U2, and the outgoing particles have polarizations U1 prime and U2 prime. Then, following the fermion indices of the top line, you would get a U1 prime bar for the outgoing electron, a factor of gamma mu from the interaction vertex, and a U1 coming from the incoming electron. You would also get a factor of U2 bar prime for the outgoing muon, a gamma nu for the interaction vertex, and a factor of U2 for the incoming muon. And they're connected by a propagator, which is G mu nu, divided by the momentum flowing along that internal photon line, which is P1 minus P1 prime squared. So does everyone understand the rules by which I derived that scattering amplitude? So this is an example of how I contracted the fermion indices along one of those lines, including this interaction vertex. And you can see that the total diagram is a scalar. Okay, we have one scalar here, or rather that has no spinor indices. All of the spinor indices have been contracted. The spinor indices here have been contracted, and you ended up with something with two vector indices that got contracted with the photon propagator. So if you wanted to write that a little more succinctly, you would write that as IE squared over P1 minus P1 prime squared, U1 bar prime gamma mu U1 times U2 bar prime gamma mu U2. And that's it. This is the scattering amplitude of an electron off of a muon via the exchange of a photon. And you should compare this in your minds to the answer that we had in Yukawa theory that we derived last time. So in Yukawa theory, we had that interaction that I called the Yukawa coupling Y. The propagator for the Yukawa theory was P squared minus M squared because the pion field had a mass. And we had a U1 bar prime U1 and a U2 bar prime U2. Okay. So you can see that there are several important differences that reflect the fact that in QED you exchange a vector particle as opposed to a scalar particle. So first of all, you have those gamma matrices that are appearing. And second of all, you have some sort of crucial sign difference here. And finally, you have no mass term here. And because you have no mass term, of course, that's going to reflect the fact that whereas the nuclear force described by the Yukawa theory was short range, it fell off exponentially for distance scales long compared to the mass scale. The Coulomb force coming from the exchange of a photon is a long range force that only falls off like 1 over r. Or the force is 1 over r squared. The potential is 1 over r. And indeed, just as we were able to determine the form of the Yukawa potential by studying the scattering amplitude, you can determine Coulomb's law. You can get the Coulomb potential from the form of the scattering amplitude. In particular, if you want to study this theory in the semi-classical limit, how does that work? Well, that means that you're essentially working in the rest frame of one of these spinors. And in the rest frame, this 4-component spinner U just becomes two 2-component spinners on top of one another. And so you can then go ahead and work out what this U1 bar prime gamma mu U looks like in that limit. What does it look like? Well, let's remember what form the gamma matrices look like. So gamma 0 was written in 2x2 block form, 0, 1, 1, 0. So in the case where you have, so you get a factor of m out front, and the case where mu is equal to 0, what do you get? You get a zeta prime dagger zeta, where zeta prime was the 2-component spinner of your outgoing electron, and zeta was the 2-component spinner of your incoming electron. So this was the case where mu is equal to 0. But when mu was not equal to 0, what did this guy look like? What was 0 sigma I minus sigma I 0? So this minus sign right here means that you're going to get a cancellation when you compute U bar gamma mu U. In particular, you'll get a zeta dagger sigma I zeta minus zeta I sigma I zeta. So you'll just get a 0 when mu is equal to I. And there's actually a factor of 2 here, because when mu is equal to 0, you got you have these two 2-component spinners here, and you get a factor for each one. So what does that mean? That means that in the semi-classical limit, what does this look like? Well, you get I-E squared over that 4 momentum. And remember, the semi-classical limit, what do the momenta look like? Well, P1 is m times the momentum 3 vector, and similarly for P1 prime, plus corrections that are subleading in the, I shouldn't say semi-classical. I mean, of course, non-relativistic limit. Someone should. So in the limit where the particles are moving slowly, and so you get, in the denominator here, what was that? P1 minus P1 prime squared. You get a minus P1 vector minus P1 vector prime squared. And what was all of this spinner stuff becoming? So what does all of the spinner stuff here become? Well, you'll get a factor of 2m times the inner product of the electron 2-component spinners, along with an inner product of the muon 2-component spinners. So what are these things telling you? These things are telling you that in the non-relativistic limit, when you exchange this photon, a spin-up electron will have to stay spin-up. You know, if, for example, you think about your 2-component basis of these spinners in the semi-classical limit, where you have, say, a spin-up electron and a spin-down electron, the fact that you get this simple inner product here, the zeta 1 prime zeta 1, just as we had last class, means that when you exchange a vector particle in the semi-classical limit, you know, you can't exchange spin between these particles. This is something that is not entirely obvious. I think it's sort of obvious in the case of a scalar exchange, but it's now the result of a computation in the case of quantum electrodynamics. So when you scatter an electron and a muon together in quantum electrodynamics via the exchange of a photon, the muon and the electron in the non-relativistic limit won't exchange spin. It actually turns out to be more complicated in the relativistic case. Okay? That's not something I'm going to work out explicitly, but there's a nice discussion of it in the textbook if you're interested in looking at it. The important point is that really from this expression here, we can now read off the form of the potential via which these two particles interact. So in particular, I remind you, as we used last class, the Born approximation allows you to study the scattering of a particle in a potential. And at leading order, the scattering amplitude is just the Fourier transform of the interaction potential. Okay? That's really just first-order perturbation theory in quantum mechanics. If you think about the case where the potential is 0, the scattering is trivial. And at first order in time-independent perturbation theory, the way that states will transition into one another, the matrix element of the transition operator is just equal to the perturbation to the Hamiltonian, which is the interaction potential. So what that means is that the potential via which these electrons and muons interact is just the Fourier transform of the scattering amplitude. And what is the Fourier transform of that scattering amplitude? Well, you'll get an e squared and an integral d3x times e to the I q dot x divided by q squared. And one can go ahead and just do that calculation. You get an e squared over 4 pi times r. That 4 pi, one has to be a little careful and include the various 2 pi's that appear when you take a Fourier transform. And there's another couple little factors of 2 that appear here and there. But basically, you could have already guessed that answer just by using dimensional analysis. So the first thing you know is that because it only depends on the absolute value of q squared here, it has to be a function of radius. And second, if you just think about dimensional analysis, q scales like, sorry, this is not a d3x. This is a d3q, of course. It's the Fourier transform. Q scales like 1 over x. So d3q over q squared scales like 1 over x. And the only thing that's a function only of radius that scales like 1 over distance is 1 over radius. Okay? So in fact, the fact that we have a 1 over momentum squared here in the photon propagator is Coulomb's law. Okay? Right? That's probably worth emphasizing. Why is there a 1 over p squared in the propagator? That's Coulomb's law. And for a massive field, if you had a 1 over p squared minus m squared, then you would have an interaction that looks like a 1 over r, but with this exponential piece multiplying it, e to the minus mr. I mean, it's quite a lot of work developing the theory of QED just to rederive Coulomb's law, but there you have it. So this combination e squared over 4 pi is going to appear quite a bit in the next few weeks. So we give a special name to it. So alpha is e squared over 4 pi. And we've seen here in a very simple diagram the first correction, or the first correction to free theory was proportional to alpha. So alpha is the thing that plays the role of the coupling constant in quantum electrodynamics. It's the small perturbative parameter. When you think about the Feynman diagram expansion as a perturbation series, you need a small parameter in order for that to be a good approximation. The fine structure constant is that small parameter. Numerically, it's about 1 over 137, at least at long distances. And as we'll see a little bit later, the fact that this number is very small, a little less than 1%, is why quantum electrodynamics is a good perturbative theory that you can use to make useful predictions. Any questions on this computation? Yes? Yeah, good. So E is dimensionless. It's yeah, that's right. That's right. I mean, I guess I've been a little bit fast here. But yes, it's about a third. If you read it off from here, it's about a third. Right? I mean, it's kind of interesting, right? Like you might expect, like you wouldn't necessarily, you might think, well, right? You know, we spent this whole time developing a perturbation theory for a theory pretending that the coupling constant here is small. Okay? But if I told you that E was actually a third, you know, you might be worried that this wasn't a very good perturbation. You know, this wasn't a very good perturbative expansion. But it's kind of this very useful fact that, first of all, you end up squaring it whenever you actually compute a scattering process, because, you know, in this example, we had two, you know, we had two interaction vertices right here and right here, so you end up squaring it. And you also end up getting factors of 4 pi from various kinematic factors. And so it actually turns out that a third is a very small number, okay, which was good for us. Good, it was good luck. But, you know, it didn't have to work out that way. And, you know, it just happens to be that the easiest, one of the most important quantum field theories is also one that's weakly coupled. You know, other important quantum field theories, as you probably have heard, are not weakly coupled. QCD, for example, is a theory where the effective coupling constant is, you know, order 1. It's larger than order 1, actually. And so the Feynman diagram techniques that we use to study this theory are only good in certain very special circumstances. Good. Another comment that I'll make. So here we discussed the scattering of, say, a particle with another particle, so an electron with an electron, or sorry, with a muon. One could also study the scattering between a particle and an antiparticle, say E minus, so say a electron with an anti-muon. So in this case, you would have a diagram with the arrows oriented in the opposite direction. So you would get an IE over P1 minus P1 prime squared. You would get a U1 bar gamma mu U1. Sorry, U1 prime gamma mu U1. But now you would have a, let's say that you would have a V2 bar gamma mu V2 prime, where V2 and V2 prime are the polarizations of the incoming and outgoing anti-muon. Again here, note that I'm contracting these guys in the only way that I'm allowed to in order to get a scalar. You know, this quantity is still a scalar here because it has the form of V bar gamma matrix times V. And now, if you remember our discussion of what these 4-component spinors look like in their rest frames, these V's in their rest frames, they could be written in terms of 2-component spinors, but with a relative minus sign. So that means that if you compared the result you would get for particle-antiparticle scattering to that for particle-particle scattering, you'll end up with a factor of V bar gamma mu V, which will be, you'll get a factor of 2m with a minus sign here. So you'll get a zeta. You'll get a zeta 2 dagger, zeta 2 prime. So this is when mu is equal to 0. But you'll get that relative minus sign here. So that changes the sign of Coulomb's law for particle-antiparticle scattering. So this is different. This is why forces that are mediated by vector fields are different from forces that are mediated by scalar fields. For the scalar field, there was none of that complicated spinor structure, so there's nowhere for a sign to come from. So this means that when you have a theory mediated by a vector particle, the force is attractive between particles and antiparticles, but repulsive between particles and particles, or between antiparticles and antiparticles. And it's really, I mean, I should just restate this just to drive the point home. This is characteristic of a force which is mediated by a vector particle, that is to say, a spin 1 particle like the photon. When we study the weak interactions or the strong interactions, which are also mediated by vector particles, W and Z bosons or gluons respectively, they'll have this exact same feature. They're attractive or repulsive depending on whether you're talking about particle-particle or particle-antiparticle interactions. Good. So I'd like to spend a little bit more time studying in more detail the scattering process. But before I do, let me pause and see if there are any questions. Yes?
Do we have universe and charge scalar field with couple field?
Yes. So scalar QED, for example.
In that case, I mean, we don't have, again, the case is field structure.
Good. But you'll still get a minus sign. Excellent question. Yeah. So actually, that's a great question. So work it out. That actually would have been a good problem. Yeah. So prove it. Good. You have all the tools. You have the power. So go ahead and show that. Yeah. Good question. Yeah. Do you know where you don't have, so, I mean, I'll give you a hint. The hint is that you didn't have these fun gamma mu's to soak up the vector indices. Instead, you had these momenta to soak up the vector indices. And when you're careful about orienting all of the momenta, you'll see that you'll get exactly the same relative minus signs. Because the difference between, remember that when we wrote down the interactions in scalar QED, which signs you got for the momenta depended on the relative orientation of the momentum and the charge flow arrow. So when you reverse the direction of charge flow, i.e. turn particles into antiparticles, you get a relative minus sign in that interaction. So if that's not clear, go back and look up the Feynman rules in scalar QED and prove it to yourself. Good question. Excellent question. Good. Any other questions? So far, we have been interested in studying the process of studying the scattering amplitude. But of course, if you want to calculate something you can physically observe, then you want to compute a cross section. So in particular, we're studying the cross section for electron muon scattering using scalar QED. Okay, that's as good as an example to work out as any. So I'll just remind you that the scattering amplitude looked like this. So U1 prime and U1 were the polarizations of the electron, the incoming and outgoing electron, and U2 and U2 prime were the incoming and outgoing polarizations of the muon. This was the scattering amplitude. And to compute the cross section, you need to take the absolute value of this. So here, I'll just let Q be this combination of momenta, P1 minus P1 prime. And you get a very complicated sort of set of polarizations. So you get a U1 bar prime gamma mu U1, and then you have to multiply that by its complex conjugate. But I want you to remember, and this is going to be important, that if you want to take the complex conjugate of an expression like this, all you need to do is reverse the ordering of this expression. So it's U1 bar gamma mu U1 prime. Okay. That's something that we used before when we discussed the gamma matrix technology. Okay. So all you've done here is you use the fact that gamma mu is a Hermitian matrix, and so, well, okay, that's something that we proved, I believe, when we worked out our gamma matrix technology. So you get a factor of U1 bar gamma nu U1 prime, and then you have to contract these with their friends, the U2s, so you get a U2 bar prime gamma mu U2 times U2 bar gamma nu U2 prime. And each one of these quantities is a scalar. So that's a scalar, that's a scalar, that's a scalar, and that's a scalar. Any questions on that so far? So it's, these expressions are going to get a little complicated, but it's important to keep track of all these indices. So this is what the cross-section is. If you wanted to compute the full cross-section, you'd have to include those various kinematic factors that you worked out, for example, in some problem sets. But what I want to do is I want to imagine that we do the following. Okay. So let's say that we don't measure the polarizations of these particles. So let's decide not to measure the polarizations of either the incoming or the outgoing electrons or muons. So what does that mean? That means that we should average over the possible initial polarizations, the U1s and the U2s, and we should sum over the possible final polarizations. So in particular, the thing that will appear in the scattering amplitude, if we decide not to measure any of the polarizations, well, let's call the polarization of the incoming electron S1, because its momentum was P1. So we have to average, so we get a 1/2 S1, sum over S1. And then we have to average over the two possible polarizations of the incoming muon, which I'll denote S2. So S1 and S2 are either 1 or 2. These are the two different labels for the two polarization states. And then we have to average, or we have to sum over the possible polarizations of the final electron and muon. So we sum over an S1 prime and an S2 prime of this amplitude, which, if you wanted to write it out explicitly, you could say depends on S1, S2, S1 prime, and S2 prime. Where here, say S1 is equal to 1 or 2, and it labels the two possible polarizations of the incoming electron. Any questions on this so far? In your problem set, you are either doing or have done something very similar for photons. Now, you might think that this is a very hard sum to do, but no worries. You've already done the sum. In a problem set that you did several weeks ago, you showed that if you sum over the possible polarizations of a spinner, so if you have a U times U bar, so if you sum over the possible polarizations of two spinners with the same momentum P, then this is equal to P slash plus M. Now here I should be a little, so this is something that you showed on one of your problem sets about a month ago. It's just some identity that you can work out involving spinors. Okay. Remember that the spinors u and u bar are functions of the momentum. And when I write down an expression like this, they're each 4-component spinors. So when I write down an expression like this is a 4x4 matrix worth of expressions. So I guess I could put spinor indices on these guys. And then this would be a 4x4 matrix. Okay. Do you guys remember working this out? I promise you did. Right. And similarly, when you sum over v's, you have an expression like this. You know, because I'm writing out the matrix indices explicitly, the ordering of v and v bar doesn't matter. You know, they're just free indices. So now I can just go ahead and apply that to this expression that we wrote down up above. So let's stare at that expression here. So in particular, I want you to just stare at this term that we have right here. Okay, you have a u1 times u1 bar, summed over spins. So let me just rewrite that here. So you end up with 1/4 times the sum over spins of this guy. Well, let me just rewrite the answer. So you get an e to the 4th over 4q to the 4th. And then you have a sum over all spins of u1 bar prime gamma mu u1 times a u1 bar gamma nu u1 prime, along with some similar nonsense for the muons. So you get a u2 bar prime gamma mu u2 times u2 bar gamma nu u2 prime. So let's just write this all out explicitly. So let's just look at this term here, just to keep life simple. Let's write this all out, writing out all of the matrix multiplication of the spinor indices explicitly. So what does that thing look like? That thing is, well, it's the sum over spins. So let's just write out all of the matrix indices explicitly. So the gammas are two 4x4 matrices. I'll call their indices C and D. The gamma mu, so we have a u1 whose index is, which is multiplied by the gamma mu. So you get a u1b because the gamma mu acts on the u1. And you get a u1 bar, that's this term here, which is multiplied, which multiplies the gamma nu from the left. So you get a u1c. And you have a u1 bar, so you get a u1 prime, which multiplies the gamma nu from the left, so that has a d index. Sorry, it gets multiplied by the gamma nu from the right, so it has a u1d index. And you have a u1 prime bar, which multiplies the gamma mu from the left, so that gets an A index. Okay. Is that more or less clear? So now we can go ahead and use these expressions up here. So when you do the sum over spins, what will you get? Well, this guy turns into P slash plus M as a 4x4 matrix with BC indices. And this guy turns into a P slash, so that's P1 slash plus M. This is a P1 slash prime plus M with DA indices when you do the sum over spins. So this whole expression, after doing the sum over spins, what do you get? You get a gamma mu times P slash 1 plus M. And then that has a C index, so that means it multiplies the gamma nu. So times gamma nu times P slash 1 prime plus M. And then the A index, that free index, gets summed over, which means you're taking the trace of that whole quantity. Any questions on that? So just to sort of recapitulate, what's happening here is I'm using these sort of convenient expressions for the sums over polarizations of these spinors. And, well, you know that when you sum over polarizations, all of the dependence on the spinor u has to disappear. It only can depend on the momentum of the incoming particle, right? Because when you sum over polarizations, you're losing all of your polarization data. So there must be some sort of expression involving the momenta, and here it is. We just worked it out using these polarization sums. So if you weren't able to follow every single step in that derivation, don't worry. You'll have plenty of chance to practice it on the problem set next week, where you study a slightly an epsilon more sophisticated version of this, where you compute electron-positron scattering. I think that's the one I did. So Baba scattering. So let's go ahead and now write down the full expression for the sum over spins. So the initial state averaged and final state summed scattering probability. So you get that friendly factor out front, and you get a trace of gamma mu. If I did everything correctly, gamma mu P1 slash plus M times gamma nu P1 slash prime plus M. And here, remember, the electron we have two different masses, an electron mass and a muon mass. So here we get the electron mass because these are electrons we're talking about. And we get a second gamma matrix trace. So you get a, this gamma matrix trace looks exactly the same except with the 1s replaced by 2s. So you get a gamma mu P2 slash plus M mu times gamma nu P2 slash prime plus M mu. Of course, this mu here is not an index. It denotes the fact that it's the mass of the muon. Now, so the expression that we have here is some function of the various incoming and outgoing momenta along with these masses. And so you know that there must be a way of simplifying this expression to remove all of these gamma matrices. You know, we're multiplying together a bunch of these gamma matrices and then taking a trace. Whatever that is, it's got to be some function just of the momenta. And there's some technology that you can use to compute these various traces of gamma matrices. So in particular, this is a fact. And it's a fact that you'll prove on your problem set, which is that when you take the trace of a gamma matrix, you get 0. Okay, that's easy to prove if you remember the form of the gamma matrices. If you take the trace of two gamma matrices, you get the metric. That's also easy to prove if you remember that you can always cyclically reorder elements in the trace. So the trace of two gamma matrices is proportional to the anti-commutator of two gamma matrices, which is the metric. The trace of three gamma matrices, well, it's not trivial to prove. That's why I gave it to you on your problem set. And finally, the trace of four gamma matrices, well, it has some expression that you'll derive involving the metric. So it's the sum of three terms involving the possible different ways that these indices can be contracted with one another. And then we can just go ahead and use these traces. We can just use this to evaluate explicitly these traces appearing in the scattering cross-section. So let's just go ahead and do that. So, for example, the trace of gamma mu P slash 1 plus ME, gamma nu P slash 1 prime plus ME, What is that? Well, the first term, the easy one to write down is the one proportional to me squared. So that just gives you a factor of 4 times g mu nu. Then you have some things involving products of 3 gamma matrices, which are linear in me. So they're me times the momentum times 2 gamma matrices. That's 0 by this expression here. And now you get the interesting bit, the part that depends on the momenta, which comes from this formula here. Okay. So let's just work that out. So this first term here, so remember that P1 slash is just P1 times a gamma matrix. So that first term here becomes just P1 mu, and the second term becomes P1 prime nu. And then you get this term here, says that you need to contract the first and the third indices together. So that means you need to contract, you get a g mu nu times a g nu sigma, which contracts the P1 and the P1 prime indices together. So that gives you P1 dot P1 prime. And then the final guy tells you that the first and the final indices get matched up. So you get a P1 prime mu times P1 nu. And that's it. And now you just need to contract that with the corresponding guy involving the muons. So when you do that, you just need to run through a bunch of algebra. So you get the sum over spins of this transition probability. Well, what sort of terms do you get? Well, you've got this guy, and you have to contract it with the exact same expression, except with 1 replaced with 2, and me replaced with mu. So from terms like this, you get P1 dotted into P2 times P1 prime dotted into P2 prime. Oh, and I forgot the prefactor. So it turns out that the prefactor, so there's a little bit of algebra. I'm running out of time, so I'll just write down the prefactor. So you get a prefactor of 8 because you get a factor of 16 here, product of 2 4s. You divide by a 4 here to get a 4. And then it turns out in order to get a P1.P2, P1 prime.P2 prime, there's 2 different ways of getting that, because you can contract this guy with its friend involving P2s, or you can contract this guy with its friend involving P2s. Put that all together, it gives you a factor of 8. And then there's a similar expression involving P1 dot P2 prime times P2 dot, or let's call it P1 prime dot P2. Okay? That comes from contracting this guy with the analogous expression there involving muons instead of electrons. Then you get the terms where you contract a term like this with a term like that. So that gives you, it turns out that there are several terms like this. So that gives you a factor of, say, me squared times P2 dot P2 prime, okay, along with an analogous term involving the muon. So there's a minus mu squared times P1 dot P1 prime. There's a minus sign because there are actually several different ways of getting this term. So you can either get this term by contracting this guy here with, let's see, with this guy, or with this guy. Okay? And if you add up the different ways of getting it, you get, let's see, you get 1 from here, Yeah, if you add up all the different ways of getting, you get 1 from here, and minus 2 from here. And I pulled out a factor of 2 already to get the 8. So that's where this minus sign comes from. And then finally, you get minus 2 me squared mu squared, which comes from contracting this term with its friend involving the muons. Are there any questions on this before I continue? So, finally, I should say that in principle, you could also get terms like that look like a P1 dot P1 prime times P2 dot P2 prime. But these all end up canceling with one another. Turns like there are no terms like that in this expression. Okay. So this is the scattering amplitude. So the full scattering amplitude say d sigma by d omega, say in center of mass frame, is found by just including all of the relevant kinematic factors. Remember that the full scattering cross-section involves this transition probability squared along with various powers of the energies and velocities of the incoming and outgoing particles. And so it's now a reasonably straightforward exercise. Just go ahead and write that out explicitly. In terms of your favorite kinematic variables. So remember, for 2 to 2 scattering, there are 2 degrees of freedom in that scattering process. You could either describe them in terms of the 3 Mandelstam variables S, T, and U, subject to one constraint, or you could describe them in terms of the center of mass energy and the scattering angle. And if you look in the textbook, for example, they give expressions where they wrote this out explicitly in terms of the center of mass energy and the scattering angle. Now, there are many, many, many expressions like that one could write down for all sorts of different scattering processes. If you look, for example, in Chapter 5 of the textbook, he sort of works through every single possible scattering process. I don't think I want to do the full kinematic details for every single possible scattering process, but I just wanted to work through this one explicitly just to, just so that you, see all of this done once. I had a bit more I wanted to say about this and a similar process. I don't want to rush, though, because this is the sort of first time that you're seeing a computation like this. And these polarization sums are very important as far as actually computing physically observable quantities. So let me just pause here and see if there are any questions. Are all the manipulations that I went through to derive this more or less clear? Because you're going to have to do almost exactly this computation in your problem set, except it'll be a little more complicated because there'll be 2 diagrams that you need to include. Yes?
I'm not sure I understand how you can get from the expression with the metrics to the
Good. So excellent. Yeah. So the point is that you have, so this expression here was this guy right here. So for example, this term here was me squared times g mu nu. And then you have an analogous expression here with all of the p1s replaced with p2s and the m mu's, e's replaced with m mu's. And so you get an expression coming from here that went like m mu squared g mu nu. And then you contract these indices here with those indices there. And you get a factor of 4. Right? And that led to this guy here. Oh, maybe with a plus sign. With a plus sign. Thank you. Sorry. Yes. One of the disadvantages of the textbook is that when he does this computation, he does various different approximations rather than writing out the full answer. So I actually had to do this myself, which means I could have gotten the answer right. But, you know, because anything's possible. No, I actually think this is more or less the right answer. Good. Yes, so did that answer your question more or less?
It's because we have the second one that...
Yeah. Good. So, any other questions? Okay. So, we could also study similar processes. So, for example, if we wanted to study the process of E plus E minus to U plus mu minus, then we have to study a nearly identical Feynman diagram. So now the scattering process is given by squaring this Feynman diagram. So here, we have an initial electron-positron coming in on the left, and muon, anti-muon going out on the right. And the amplitude, as you can see, well, if you look up at this diagram here, it's the exact same thing as this diagram, just turned on its side. I've just turned it 90 degrees. So that means that your answer for the scattering amplitude is going to be exactly the same. But the only thing that we need to be careful about is that we always use the normalization where the incoming and outgoing momenta move from left to right. Okay? So that means that you have to take P1 going P1 prime going to minus P1 prime, and P2 going to minus P2. Because we've exchanged one of the incoming electrons, an outgoing electron with an incoming positron, and an incoming muon with an outgoing anti-muon. Okay. And in fact, if we wanted to go ahead and write out what the cross-section looks like, the answer for the cross-section is a little bit simpler. And the reason why the kinematics is a little bit simpler is that for the process of an electron scattering off of a muon, you have two initial particles with opposite mass and two initial particles that don't have equal masses and two final particles that don't have equal masses. Whereas it's much simpler to study two initial particles with equal mass and two final particles with equal mass. The kinematics just looks a little simpler. And so that means that when you write out the cross-sections, the answers that you get are a little bit simpler and have a sort of nicer sort of physical interpretation. And so I thought what I might do, I was planning on doing it now, but I'm already out of time. So maybe what I'll do at the beginning of class next time is just write out explicitly what these cross-sections look like, because there's a lot of physics that you can extract for them. I mean, there's a ton of interesting physics that you can extract for them. And so maybe, I don't want to, I have a lot that I want to cover before this class ends, but I don't want to rush things. So maybe what I'll do is I'll just stop here, and next class we can start by writing out these cross-sections. But maybe before I end, I'll see if there are any other questions. Yes?
When we did the sum over the spins, there were like, if you restored in the formula, if you restored the spin indices, it would be like different indices for the different scalars that are there.
Sorry, different indices. So which expression are we talking about?
At the beginning, when we started to sum over the spins,
Uh-huh.
when we did the amplitude first. Yeah, here. So if we restore the indices, we will see
You mean-
in the first brackets,
Yeah.
it's a different
You mean
index.
like S? Yes.
So how does it?
So which indices? The spinner indices?
Spinner.
Yes. Yeah, yeah,
How
yeah.
does it like just go to the same indices for using the formula which we at the problems a long time ago? So
I'm not. Maybe I don't quite understand what
here
you're.
in the formula
Mhm.
is the
So in this-
sum over the same indices with the u and the bar.
Yes.
Then both in the index s.
Yes.
But above there's like a different.
Right.
thing.
So if we wanted to write this out explicitly, I see exactly what you're talking about. This guy has an S prime index. So this has an S1 prime. This one has an S1. But remember, we got this expression here by squaring it. So this has an S1 prime index here. This guy has an S1 prime index here. This guy has an S1 index, and this guy has an S1 index. Remember, when you square it, you get 2 factors of each u. Yeah, it's kind of magical, right? Like, they also have the same momenta, right? This guy had momentum P1 prime, and this guy had momentum P1. When you square it, you get 2 factors of this guy here. With momentum, it's the same spinner, right? U times U bar.
Okay, guys.
Sure. Good question. Good. Any other questions? Great. Okay. So I think next class what we'll do is we'll talk a little bit more about the nitty-gritty of what these scattering cross-sections look like for, say, electron-positron annihilation. And also we'll talk a little bit about Compton scattering. Good. Okay. See you next week.